In this video, we're going to be looking at the equations of kinematics for constant acceleration. The simplest kind of accelerated motion is constant acceleration in a straight line, and that's what we're going to start with. And when I mean constant acceleration, you should be thinking that the velocity of the object is changing by the same rate throughout the whole entire motion. Before we jump into the mathematics of these equations, let's kind of get a picture of what's happening. Let's draw a motion diagram of something that is undergoing uniform acceleration. For example, imagine you have a car that is traveling down a straight section of the highway and speeding up at a uniform rate. Let me put in some numbers, for example. So maybe at 0 seconds it's going 5 meters per second, and then at 1 second it's now going 10, and then at 2 seconds it's going now 15 meters per second. So it would be accelerating in the positive direction, and you could calculate the acceleration by, for example, using the definition of acceleration, which is the change in velocity over the change in time. And you could figure out the change in velocity, say, over the first time interval would be, say, 5 meters per second. We did 10 minus 5, which gives you 5 meters per second. And this would be over a time interval of 1 second. So the acceleration would be positive 5 meters per second squared. That would be from 0 to 1. And then if you were to continue from 1 all the way to 2 and find out the change in velocity over that time interval, you're also going to get an increase of 5 meters per second over 1 second. And again, you have the same acceleration. So this is what we mean by constant acceleration. It is at the same accelerated rate all the way through its motion. If we were to plot this motion here on a velocity versus time graph that you can see down here on the bottom left of your screen, you can see that that actually is going to give you a nice straight line. And straight lines, remember that the slope of a velocity time graph represents acceleration. So if you find the acceleration at this particular point here or over here, it's going to be the same slope. And so whenever you get straight lines in a velocity time graph, that means you have constant acceleration. So these kinematic equations that are listed over here can be derived from some fundamental concepts that I'll get into in a moment. But before I get into the mathematics of everything, I think it's helpful to understand what each of these variables represent if you don't already know that. So let's take a look at this diagram and maybe indicate what all these variables would be in a diagram. We're going to eliminate one of the pictures here, so we'll go from a starting position, say, to this final position over here. So whenever you see this v sub 0 here, this represents the initial velocity at a time t sub 0 equals 0 seconds. So it's the velocity at time 0. And then whenever you see just v by itself, that's the velocity at some point in time. Now you could label this and write a little 1 here or 2. We'll later do that when we deal with things in different stages. But for now, you could just write v, and that will be implied that's the final velocity at some other point in time. I've also represented the acceleration going forwards here, and t in here. Now t represents really the time interval. So when you see t, you should be thinking of as delta t, which would be t minus t sub 0. In most cases, you're going to be starting your initial time at 0 seconds. The other thing we should talk about is the position. This refers to the final position of the car. So this we can maybe label over here as an x, and then over here will be x sub 0. That's the initial position. Normally, you'll find it to be a little easier to make the initial position 0. So basically set your origin here to be 0, and we also normally make, say, to the right, this direction, this will be along the positive x-axis. Sometimes in the equations you'll see this x minus x sub 0. This is also rewritten as just simply delta x, which is the final position minus the initial position. Just like we learned earlier, the change in velocity would be the final velocity minus the initial velocity. Now these four equations are very important. You'll be given this equation, and this equation on your formula sheet. You do not need necessarily number 4, but it is helpful in problem solving. You are expected, by the way, to know these. All right. Remember, on the multiple choice section of the exam and the test, major test that we have, you will not be allowed to use a formula sheet. So you have to know these formulas for that section. Furthermore, while we're doing some quizzes in this section, I will also not allow you to bring a formula sheet. So you'll have to know them for the quizzes as well. So I find it helpful to derive these equations in helping you remember them. So if you can derive them, or you know the process at which we derive them, maybe that will help you understand where they came from, and you'll remember them more likely. The first one's very easy, really. If you think of these equations, they actually really stem from two main ideas. They come from definitions of two things. One, the definition of acceleration, which is the change in velocity over the change in time. And then we also learned the definition of the average velocity, which is the displacement divided by the time interval. So we're really going to be using that. So let's go down to derivation number 1 here, and we're trying to prove that equation. Where do you think this comes from? Well, hopefully you're looking up here and thinking of the acceleration definition. The acceleration is defined as the change in velocity over the change in time, where the change in velocity is the final velocity minus the initial velocity, divided by delta t, but delta t is just really time. So we're just going to put t for that. And if you cross multiply, you're going to get the acceleration times time is equal to the final velocity minus the initial velocity. And then rearranging the equation, we can have velocity is equal to the initial velocity plus acceleration times time. And there you go. There's the first equation. But I like to point out one thing. There's a reason why I put that graph here on the left side. Take a look at that graph. This is a graph of velocity versus time. This is really just a line, which you could think of as y equals mx plus b. But in this case, on the y-axis, we're plotting velocity in the x direction, or we could just write v. So you could replace the y with a v. The slope. What's the slope of a velocity versus time graph? You learned that earlier. The rise is the change in velocity. The run is the change in time. So that's acceleration. So you can replace the m with a. And along the x-axis, we're not plotting x, we're actually plotting time. So let's replace the the x with the t, actually, here. And then finally, the y-intercept of this line. That's going to intersect at time 0. That's the starting velocity. That's the initial velocity. So let's replace the y-intercept with v sub 0. And if you rearrange this equation, you're going to get that. All right, let's move on to this equation here, number 4 in our list, and let's derive that. Now this one comes from the definition of average velocity. Remember, average velocity is the displacement divided by the time. But since the velocity changes at a uniform rate over time, we can use as well the average velocity is the average of, say, two different velocities at, say, here and another point over here, the final velocity. So we could take the final velocity, v, plus the initial velocity, v sub 0, and then take the average of those two, so we'll just divide that by 2. Be careful with this because this is not in general true. This just happens to be true with constant acceleration. So let's rearrange this equation now and write delta x equals the average velocity times the time interval delta t, which we'll just simply call t. And then let's substitute this in here, and so we're going to get the displacement is equal to the final velocity plus the initial velocity over 2 times the time t. And there we have equation number 4 proven now. Okay, let's move down to number 2 now. And there's probably different ways of proving this. It's really, maybe you should stop the video at this point and see if you can do it. You can now use any of these equations to try to prove this one or this one. All right. Um, if you're stuck, then listen on. Okay. I'm going to start off with this equation here. I'm going to start off with delta x. So the reason why I'm starting with that is because I know delta x is x minus x sub 0, and I see that here. And I have delta x equals v plus v0 over 2 times t. And I'm looking at this equation and I'm thinking, well, I don't have any final velocity above here, so I need to get rid of that final velocity. And I need to get the acceleration in here somewhere. So hopefully you're seeing, oh, we could substitute in, we're going to sub in v equals v0 plus at into this equation. For v right here, we're going to substitute it with all of that. And we also know that delta x is really just the difference between the final position minus the initial position. So let's replace that as well. So we have x minus x sub 0 equals, in brackets here, v sub 0 plus at plus the other v sub 0 all over 2. And this is multiplied by t. Let's do some combining over here. I have now 2 of these. And then to get rid of the brackets and bring over this x sub 0 to the other side. And you should get the final expression right here. And there's a reason why this graph is shown over here to the left. Again, if you plot now the position versus time of something that is undergoing uniform accelerated motion, you'll find that you're going to get a quadratic. The initial position here is shown x sub 0. And then this is the effect of the acceleration where that starts to slant upwards. If we didn't have any acceleration, then the motion would just be going like this, which would be at a constant velocity. So in the end, we get a quadratic when we plot x as a function of time. Hopefully you can see this and relate it to this graph. Okay, one more to do. Maybe you want to stop it, give it a go, see if you could do it on your own. I'm being too kind. I'll let you do this on your own and then show me in class.